Estamos en vivo.
Muy buenas noches a todos, socios de la Asociación Mexicana de Geofísicos de Exploración. Es un gusto para mí estar en la primera reunión de charla técnica de esta gestión de la mesa directiva del bienio 2020-2022.
Estamos en
Me
vivo.
hubiera gustado en esta ocasión presentar
Muy buenas noches
trabajo, pero estamos
a todos
en el periodo de transición
de la Asociación Mexicana de
y lo vamos a
Geofísicos de
extender un poco
Exploración.
más. En esta
Es un
ocasión,
gusto para mí estar en la primera reunión
con la distinguida
de
presencia
charla técnica
del
de
doctor
esta
Castagna,
gestión de la mesa directiva
que no
del
deja de
bienio
sorprendernos
2020-2022.
por las innovaciones que introduce.
Estamos
el
en
Me hubiera
mercado de la
gustado en
geofísica.
esta ocasión presentar
Muy buenas
una charla
noches,
por
pero
demás
estamos
interesante
a todos
en el periodo de
socios
transición de la
Se
Asociación
habla
Mexicana de
de que lo vamos a
Geofísicos de
extender un
Exploración.
poco más. Otros tiempos no
En
nos
esta ocasión, para mí estar en la primera reunión con la distinguida charla técnica de esta gestión de la mesa directiva
que no deja de
bienio
sorprender información
2020-2022. Me hubiera gustado en esta ocasión presentar una noche por demás estamos a todos en el periodo de transición de la Asociación Mexicana de Geofísicos de Exploración.
Otros tiempos ustedes, el doctor
En esta ocasión, para mí estar en la primera reunión con la distinguida charla técnica de esta gestión de la mesa directiva
que no deja de
bienio
sorprender información.
2020-2022.
Muchas gracias,
Gustavo, en esta ocasión.
Buenas noches, distinguido panel, socios e invitados. Gracias por el espacio. John Castagna tiene un grado de bachelor en geología y un máster en geoquímica, ambos por el Colegio de Brooklyn de la Universidad de Nueva York. Obtiene también un PhD en geofísica de exploración por la Universidad de Texas en Austin. Actualmente, el doctor Castagna tiene la titularidad de la cátedra Robert Sheriff de Geofísica de la Universidad de Houston, máster en Geoquímica, y es el fundador de los Physical International de la Universidad de Nueva York. Previamente, fundó y fue el primer presidente de Fusion Geophysics. John tiene más de 30 años de experiencia en geofísica de exploración, trabajando en diversas áreas del conocimiento como explorador, investigador, el manager de Houston, profesor y hombre de negocios. Dirigió el Instituto para la Exploración y Desarrollo de las Geociencias en la Universidad de Oklahoma y dirigió la investigación de análisis sísmicos para la compañía petrolera Arco. Además, trabajó en gran variedad de proyectos de exploración y desarrollo nacionales e internacionales, conociendo a Mike Bastel, entre otros, y desarrollando la ecuación para la determinación de la velocidad de ondas de corte, que la distinguen a nivel mundial como la ecuación Castagna. Dr. Castagna tiene más de 150 publicaciones en geofísica de exploración. Sus dos publicaciones de la SEG sobre ABO son bestsellers y textos obligados en la educación geofísica de las universidades. John es bien conocido por sus contribuciones en física de rocas, análisis ABO, descomposición espectral, inversión sísmica e interpretación sísmica cuantitativa de alta resolución, entre otras. Finalizo mi intervención con una anécdota de mi apreciado advisor en el PhD. John cursó sus estudios de doctorado en la Universidad de Texas, bajo la tutela de Milos Backus, donde obtiene un amplio conocimiento en geofísica de exploración y procesamiento de señales. Pero quizás de lo más relevante que John reporta acerca del profesor Backus fue: él me infectó con su amor por la geofísica y me mostró cómo encontrar simplicidad en la aparente complejidad. El encontrar simplicidad en la aparente complejidad ha sido un sello de las contribuciones de John a nuestro campo de la geofísica de exploración. Esa misma simplicidad la encontrarán en la plática de esta noche, con la última aportación que nos ha brindado el doctor Castagna, la descomposición de fase. We welcome our lecturer tonight for teaching his presentation, Phase Decomposition, Theory and Applications. John, we're really glad for having you here to teach your presentations to AMGE community. We really appreciate your participation and contribution to our knowledge in the science of the exploration geophysics. A los queridos escuchas, la tónica de la plática va a ser que John expondrá su exposición Y las preguntas que ustedes deseen hacer, háganlas por favor al chat sobre la marcha que vaya a la presentación, para una vez terminada esta, puedan leerse estas preguntas para que el doctor Castagna tenga el gusto de poderlas responder. Muchas gracias. Go ahead, John. You can start whenever you want.
Okay, thank you, Ephraim. It's a pleasure to be here. Let me share my screen and bring up my presentation. And please let me know if everybody can see this.
Not yet.
You're not seeing the presentation?
No.
Yeah? Nothing?
No, no.
Okay, let me share the screen again. Maybe I did something wrong. How about now?
Okay. Right
yes? Now. Okay. Very good. Well, it's a real pleasure to be here. I want to thank you very much for the very warm welcome. I have many good memories in Mexico, and I'm very pleased to present a unique new technology called phase decomposition. I want to emphasize that phase decomposition is not phase rotation, and it's not an instantaneous phase attribute. It is a new way to decompose seismic data. Similar to spectral decomposition in the sense that with spectral decomposition, the seismic trace becomes a sum of sinusoids. Well, instead of a sum of sinusoids of different frequencies, in phase decomposition, the seismic trace is a sum of waveforms with different phases. And there's something very unique about some of these different waveforms that a seismic trace can be decomposed into. In particular, when we have thin layers, there is a very unique characteristic of the effect of hydrocarbons. And that is the hydrocarbon effect. Let's see if I can get my pointer. My hydrocarbon effect here is always in the minus 90 degree phase component that I decompose a trace into. What I mean to say is, if I have a waveform caused by a thin brine sand, meaning by thin I mean below seismic resolution, and I compare that to the waveform where I fluid substituted the brine with gas, so the only difference here is the presence of hydrocarbons. That difference I call the hydrocarbon effect. And if we look at that waveform has a unique phase characteristic in that it's minus 90 degrees. This waveform is always anti-symmetrical. So anytime you have a thin layer, introducing hydrocarbons increases the magnitude of the minus 90 degree phase component of a seismic trace. Now, that's not the only thing that will increase the minus 90 degree component. Any drop in impedance will also manifest itself for a thin layer in the minus 90 degree component. So phase decomposition is also an excellent way, as I'll show you, of mapping subtle impedance changes that you otherwise would not have seen. So the trick then is to take any waveform and decompose it into phase components. And that's what we're showing here. The wiggle here is a seismic trace, and the panel on the right is, instead of a time frequency analysis, it's a time phase analysis, where the horizontal axis is phase from minus 180 degrees to positive 180 degrees, and the colors are the amplitude. So you can see this event here is coming in at somewhere around minus 100 degrees. So you can see that every event on this waveform has its own unique phase characteristic. And unlike a phase attribute, we can represent the phase and the amplitude at that phase simultaneously. For the instantaneous phase attribute is independent of amplitude, but the phase components carry the amplitude associated with that given phase. So therefore, it's really excellent at responding to impedance changes. So just to show you the value of doing this, this is a Gulf of Mexico data set, and it's an area where there are typically bright spots. And in layers that are below seismic resolution, we expect hydrocarbons to produce a leading trough. The troughs are blue here, so that's a negative response. A leading trough followed by a peak. So that's a characteristic attribute in this area of hydrocarbons. Now, unfortunately, even though that is a characteristic attribute, it's sometimes very difficult to sort out. And sometimes there could be misleading responses. For example, down here, we have a leading peak here followed by a trough. So this is in what otherwise would have been a nice trapping situation. But the leading peak would have caused one to be a little bit pessimistic about that prospect. All right, well, now we're going to decompose into different phases, and we're going to look only at the minus 90 degree phase component. And there we have it. And you can see these are all beautiful troughs over peaks. So these are low impedance anomalies. They have the right polarity and the right amplitude to be caused by hydrocarbons. Now, this doesn't mean that all of these anomalies are hydrocarbons. Some, for example, could be low saturation gas or just very porous sands. But the point is that we have made things prospective, such as this, that previously would not have been very prospective. Plus, we have a much cleaner section. So we've essentially filtered out the lithological reflections that could not be caused by gas, that have the wrong phase to be produced by hydrocarbons. And we have passed through those signals which have a good likelihood, or at least the right characteristics, of being caused by hydrocarbons. Now, it turns out that this change in impedance caused by hydrocarbons, in the case of bright spots, always appears in the minus 90 degree phase component. So here we have a simple case. I have a simple layer. In brine, I'm representing the impedance in white. In red, I have the hydrocarbon saturated impedance. And we see a drop in impedance in that layer. The reflection coefficients for the gas sand in this case are a strong negative over a strong positive. But the brine sand was also low impedance, so it was negative. So it's also minus 90 degrees. But the difference, as is always the case, is minus 90 degrees. Let's go to a bright spot situation, a dim spot situation, where the sand is high impedance. I add gas, I lower the impedance. So I go from a positive pair, positive over negative for the brine sand, smaller positive over smaller negative for the gas sand. But again, the difference is minus 90 degrees. In fact, for any combination, this is a polarity reversal. Again, the difference is minus 90 degrees. And finally, a more complex impedance situation where we have a stair step. Again, the difference is minus 90 degrees. Now, I've shown you some very simple models, but in more complex models, as long as we're below seismic tuning, this relationship holds. Now, if we're so unlucky as to have a reservoir that is much thicker than seismic tuning, I'm being facetious, that's a good thing when we have such a thick reservoir, but for our analysis, we can push it below seismic tuning by low-pass filtering. So we will sometimes do a spectral decomposition first and then do phase decomposition at different frequency bands to see the hydrocarbon effects on layers of different thicknesses. So to summarize to this point, different seismic responses tune up differently for different phase components. Seismic amplitudes are strongest and most anomalous at the phase of the reflection coefficient anomaly, and the amplitude for individual phase attributes. And as I'll show you, they can reveal subtle anomalous behavior that otherwise would not be observable. And I'm going to show this with a channel example. I have a thin layer with a shale above, a shale below, and I have an interchannel area with a certain impedance, and then I have a channel in the middle here with slightly lower impedance. So it's a small drop in impedance. If I look at the conventional synthetic, so a normal incidence synthetic, which would be a typical type of stacked response, I've indicated here with the red lines the extent of the channel, and so out here we have the interchannel area, more interchannel area here, and here we have the channel itself, and that is a very, very, very subtle change on the data that you tend to look at every day. So on typical seismic data, you would not be able to, odds are you wouldn't be able to see that channel. So now we're going to look at the same channel, but on the minus 90 degree phase component. So we take this synthetic and we do a phase decomposition and then display the minus 90 degree phase component. And there it is. And suddenly we have a large impedance anomaly, we have a large amplitude anomaly associated with that small change in impedance, which now reveals the extent of the channel. And I'll show this on real data in a bit. Now, as I said, for this effect to be applicable, we have to be below seismic tuning. So here is a seismic wedge model. So we have a pinching out layer here. We go below tuning, it's a low impedance layer, so it becomes a trough over a peak here. And above tuning, we have individual responses. So these are the phase of the wavelet, which is 0 degrees here. And we do phase decomposition, and look what happens. The minus 90 degree component shows the thin part of the reservoir. The zero phase, well, actually 0 and 180, both of those phase components summed together show the thicker part of the reservoir. Now, in this case, we're showing a synthetic example of a water contact, and it's a polarity reversal. So down dip, we're high impedance, so it's peak over trough. Up dip, we're low impedance, it's trough over peak. Where we have the water contact, we have the phase changing laterally as the thickness of the wedge of water and the relative amounts of gas-filled rock and brine-filled rock change. All right, so there's a continuously changing phase in here associated with that water contact. Remember, we're below tuning, so we're not going to see a resolved water contact. We'll now do phase decomposition. And here we have the phase distortion caused by that water contact. So this is the change in the amplitude on the 0 degree component caused by that flat spot or by that flat contact. It's not a flat spot, it's the change in the waveform due to that flat spot. So it's actually not flat, but it shows the lateral extent of the contact. And if we look at the plus and minus 90 degree phase components, we see the up dip hydrocarbons and the down dip high impedance brine sand. So let's see how this works in practice. Here we have an amplitude map in the Gulf of Mexico. Again, this is a bright spot area, and we look for bright amplitudes here. But experienced hydrocarbon hunters here know that if we're going to have a bright amplitude, that means I have a low impedance reservoir. That means I should have a trough over peak response. Now, this line, this dashed line is this inline here, and the amplitudes are just an RMS amplitude over the window, so I'm catching all the amplitudes and their spatial distribution. Now, the operator of this field decided that they wanted to drill this amplitude here. However, if you look at the section, this amplitude is associated with these. Here we have a peak over trough that is looking like it should be high impedance layers, maybe hard streaks of some kind. So that bright amplitude doesn't seem to be acting like a hydrocarbon indicator. However, the operator was insistent that they drill this. Well, it turns out that they did drill it, and it was pay. So the experts, and had I been a consultant on this, I would have told them to be cautious here. The experts would have been wrong, and they would have been right for drilling this. This was pay. So once you see that this is pay, what about all these other amplitudes? Is this yellow good here? Is that yellow? It's even brighter. It looks even better. What is the extent of the good amplitudes? Are greens hydrocarbons as well? Is all of this perspective? Well, one of the beauties of phase decomposition is it gives you a different view of the same data. So you could see things from a different perspective. So now we'll look at the minus 90-degree phase component. And look at this. There is an amplitude there. It's smaller than previously believed. But in fact, the phase decomposition is saying, yes, that's a good amplitude there. It also, if we go back to the other section, this amplitude here is turning out to be good. But there was a strong amplitude in here, which in fact, the good amplitudes are to the south. And there was an amplitude there, which clearly has the wrong phase. So the value in phase decomposition is it shows you a completely different perspective of where you have hydrocarbons and the areal extent of those hydrocarbons. So it's important both for prospecting and for volumetrics. Okay, so let's look at a subtle change in waveform caused by a channel. And so here we have the original seismic data on the right, and the event of interest is here. And then you see a faint white line there. It looks like someone badly picked that event. In fact, from my point of view, those are the correct picks. They're on different parts of the waveform, but that's because as the rock properties change laterally, where on the waveform you should be picking is changing. We love, because it's easy to just snap on a peak or a trough, but anytime you've done synthetics, you know that the actual top typically doesn't occur precisely on a peak or trough, and in different wells it occurs on different parts of the waveforms. So this is an ambiguity that on the original seismic data, there's no way to really know where you should be picking on that event, especially if you don't have nearby wells. Well, we'll look at the plus and minus 90-degree phase components here, and instead of nothing interesting happening along that horizon, here you see a big anomaly in the middle. That happens to be a channel. It's showing low impedance. It's blue is soft, red is hard here, so that's a low impedance channel, and on the edges here, it goes to high impedance interchannel area. Now, if we go to the zero phase component, I could pick that peak. So if I pick zero phase here, that peak corresponds to a zero crossing on the 90-degree section. And so now I'm picking on a constant phase, and that's the pick that's superimposed here. So even though the waveform phase is changing laterally, by picking on a constant phase, then we are on a consistent horizon that's being picked that is not changing then with the rock properties. We've had a lot of good luck with this technique. It's been applied in Mexico, and you know, I'm not privy to show you that right now, but we've applied it all over the world. But some of these have been released, and this is offshore Brazil. And it turns out that there's a major field on this section, and you can see amplitudes, and the production is associated with these amplitudes. I think you could see feeder channels and fan-like geometries here. But there are also amplitudes, for example, this sinuous thing. Well, it turns out that wells in here were dry holes. Wells in here were good. Well, let's look at what the phase decomposition tells us. And the phase decomposition now has discarded the amplitudes that were dry holes and leaves only the field. And where did those amplitudes go? Well, they're in the 0 degree component here. So again, this is a way of filtering away amplitudes that have phase that would not be prospective for hydrocarbons. Here's an example in the Gulf of Mexico from one of our clients, but I could show it because it was published. And here we have an amplitude anomaly, and it's basically a three-way closure against a fault. Looking on the stack section, it looks like this whole thing is good. However, on the minus 90 degree component, the northeastern bit of this is gone. And where did that go? It's over here in the 0 phase component. In fact, the client mapped a fault right in there. So these amplitudes in this part of the field have a very different phase than the amplitudes at this part of the field, suggesting that there are major changes happening across that fault. We've used this technique with good success. A lot of examples in China where we're looking for porosity in carbonates. And this is a case where the seismic amplitude is not correlated to porosity. These are porosities in wells, so each one of these is a well. And in fact, these are high impedance layers, and as the porosity is increasing, the amplitude is hardly changing at all of the seismic data. On the other hand, if we look at the plus 90 degree phase component, we see it acting like a dim spot. The higher the porosity, the lower the impedance, the lower the amplitude on the plus 90. So this trend is making perfect physical sense, and it's correlating very well to the carbonate porosity and could be used to differentiate potentially productive wells from tight wells that won't flow. The implications for this pre-stack are really amazing. One of the great complications of AVO analysis that people tend not to talk about is the fact that the tuning effect is offset dependent. Even though I have a move-out corrected section, the actual time thickness of the layer decreases with increasing offset. So if I'm in the vicinity of tuning, the tuning effect, if I'm below tuning, at or below tuning at near offset, it will suppress the AVO anomaly as I get thinner and thinner. And stretching it doesn't fix. NMO stretch doesn't fix that problem. Alternatively, if you were well above tuning at near offset, you could possibly create a false anomaly by tuning up at far offset. So offset dependent tuning is a major problem in AVO analysis, and it's generally not well handled by the techniques that we have. On the other hand, I could take this gather, this is synthetic, so I know the answer, I know there are hydrocarbons here, even though it's a subtle change in amplitude. By the way, this is the Hampson-Russell data set that they provide with their software. So it's a very well-known data set, very famous. Even though there's a very subtle AVO anomaly here, a subtle amplitude increase with offset, on the minus 90 degree component at the far offset, I would call that a screaming anomaly. The amplitudes at far offset are exactly the right phase to be caused by hydrocarbons, strong trough over a strong peak, and the change in amplitude with offset is enormous. So this becomes a very robust, from a very subtle effect, it becomes a very strong effect on the phase decomposition. And we could see that on the real data. This data set, in fact, since it's distributed with Hampson-Russell software, I have been using it in my courses for about 20 years. And I always viewed this as a topographic high. I felt that, yes, it was a channel here, and there might be differential compaction around the channel, the sands being less compacted, so this being a topographic high. That was the way I looked at it, but that's a little problematical with the event underneath being absolutely flat. I hadn't really thought about it enough. I was just calculating AVO attributes, and I was able to find AVO attributes that showed the anomalous behavior, but I really didn't understand what was going on. I hadn't given it enough thought, and I hadn't modeled it enough. Well, if we look at the minus 90-degree phase component, it shows you the extent of the reservoir. Of course, other events could have minus 90-degree as well, anytime you have an asymmetry in the reflection coefficients. But here you see the extent of the field, and you see down dip, the minus 90-degree component disappears. In fact, what is happening is here, you have a polarity reversal here. You don't have a structural high. This is not high relative to that. It's just a different, the waveform shape has changed where you have the channels and the hydrocarbons in the channels. So anyway, there it is on the minus 90-degree phase component. If we go back and look at some more synthetic models, there is another fundamental ambiguity in AVO analysis that people talk about, and that is the ambiguity between the rock properties of the layer, in particular the Poisson's ratio of the layer, and the apparent move-out in the layer. So I'm going to show that problem here, and it's synthetic data, and we know the velocities perfectly, so we know the move-out perfectly. So the move-out is perfect. Here's a brine sand case, and you can see it's an amplitude decrease with offset, and it's been moved out correctly. Not a problem. Now I'm going to show you the gas sand synthetic also with the correct move out. This is what the event should look like as a function of offset if you move it out properly. In fact, it looks like a move out error. And if you were being very careful as a processor, you might run residual velocity analysis to flatten this event. You might run trim statics. You would force that event to be flat, and what have you done? You've killed your AVO anomaly. The AVO anomaly is actually a change in amplitude from positive here to negative there. So that's a polarity reversal that is subtle because it's a thin layer. So it manifests itself as a change in phase with offset. Well, this seems like a fundamental problem. How would you get around this? How would you fix this problem? Well, what I'm going to do now is I'm going to do phase decomposition on this gather, all right? So this gather with the apparent move-out error in it, and I'm going to look at the zero phase component. Perfect move-out. So in fact, if you want to move an event out correctly, you should be doing your velocity analysis on the zero phase component. So anytime you have a polarity reversal in your data where at near offset you have a positive reflection coefficient, at far offset you have a negative reflection coefficient, to get the correct move out, you should do phase decomposition first. And if you look at the minus 90-degree phase component, once again, we have the strong amplitude anomaly at far offsets that was not apparent before. So really, phase decomposition can revolutionize our AVO analysis. Okay, I wanted to show you what could be done with Luminous software, and this video had voiceover. It was a demo, but in fact, the video is not working, and I can't quite access it now. I should be able, when we test, okay. The sound doesn't work on the video, but I'll be able to advance and kind of talk over it, I hope. Let's see. I had it for a second, and now I can't do it for some reason. We tested it earlier today, and it was working. Okay, well, here we have a seismic section, and here we have a phase gather at a particular trace. And you see the different events have different phases. And the idea was to show you what a channel response would look like. Oh, hold on. Let's see. Maybe if I turn my pointer off. Let me just try one last thing. Go all the way to the bottom here. I wonder, okay, we can see it in this view now. All right, so rather than show the video as is, I'm going to just advance through it. And we're just seeing various looks through the data. We're moving through the data, and we're seeing our different phase gathers. Remember, the phase gather is minus 180 on this side. Hold on. Oh, sorry. Okay, not what I meant to do. We have a phase gather over here, and the next thing we're going to try to do, let me go back and let me try this again. I'm really screwing this up. Let me try it one more time. And I'm going to try to advance through this. Again, these are phase gathers with phase at different events. And here we see some channels with spectral decomposition. We're going to isolate the phase in these channels. Going to move through this. Here we have a distinctive phase associated with the channel. This is plus 90 degrees. This is reverse polarity data. And if I advance a little bit more, we're going to track this event. And there's the channel. Let's see if we could, there we go. So we've been able to track the distinctive phase associated with this event and produce a beautiful channel anomaly. Anyway, I hope that last bit was not too confusing, but we have time for questions. I'd be happy to entertain any questions you have.
Thank you very much, John.
Yes. Okay, John, I have a few questions. First question from Gerardo Clemente regarding the processing sequence and the effect of the processing sequence in the phase response.
Yes.
Especially on onshore data and the static solution.
Okay, very good. So one thing I neglected to say, in looking for the minus 90 degree component, we've assumed here that the wavelet phase is known and it's zero phase. So we assume that the data has been zero phased first. If your wavelet is not zero phase, for example, if it were 30 degree phase, instead of looking at the minus 90 degree phase component, it would have to be the minus 60 degree phase component. So a fundamental aspect of all of this, and again, we're looking for subtle anomalies, so signal to noise ratio is going to be an issue. So we assume good processing, and we assume phase and amplitude controlled processing. Improper statics, if improper is if such that it distorts the phase of the signal, for example, different static correction at different offsets, producing a summation which has the wrong phase, that would interfere with the process. So we always like to watch the processing very carefully.
Great. The second question from Edilberto Román Hernández is related to, is it possible to differentiate gas-filled sand from volcanic products?
Well, typically, yes. Typically, the volcanics will be high impedance, so you should see those on the plus 90 degree component, and the hydrocarbons are on the minus 90 degree component. In fact, in looking at the data, and I did have this problem in Mexico out of the Veracruz office, there was a volcanic event which, if you just look at the data, it seemed to be the wrong polarity to be volcanic. So something to do with how it's interlayered, the sequence of reflection coefficients produced a misleading looking phase. And so it would be very interesting in a case like that to see if the phase decomposition could separate that out. And we'd have to try it to know.
Great. Reynaldo Castellano, he's asking what processing condition on the phase should be done during the processing.
Yes, so, you know, one thing that is a little bit ambiguous is the Q attenuation. As the wave propagates, it's going to be changing its phase, and it is possible to do Q compensation, but there's a tendency for that to, as you get deeper into poorer signal-to-noise ratio, that tends to blow up noise. And so what we like to do is we like to provide Q phase compensation. In other words, correct only the phase for the Q attenuation and not blow up noise at high frequencies. But yes, again, anything that will produce a blurry event that causes your event to not be focused well will distort the phase also. So the more carefully we watch the processing, the better chance of producing consistent phase in our data that is interpretable the way we would like it to be.
Okay. Moisés Cochea has a question on does it work in the dead domain?
Yes. One of the beauties of phase decomposition is it's not an inversion. It's just looking at the waveforms themselves. And so, in fact, we don't use the seismic wavelet. We don't need an estimate of the seismic wavelet, only to the extent that, you know, we've done synthetics and we're convinced that the wavelet's zero phase, you know, where we have wells. But to the extent that the wavelet is zero phase, we don't need a time and spatially varying wavelet, especially if we start going into complex structures. And as we get away from well control, being sure of the wavelet is very difficult. This is not an inversion, it's a decomposition. So we don't have to know the seismic wavelet as long as we are safe in assuming it's zero phase.
Humberto Arevalo, do you estimate the phase decomposition mathematically?
Yes, in fact, the phase decomposition is a unique transformation. And so the only ambiguity is how events are recognized. But once an event is recognized, the decomposition of that event is an exact mathematical relationship.
Okay. Euro Bermúdez, the phase decomposition looks good in plastics. How about carbonates? Can you differentiate phases in carbonates?
Well, as I mentioned, in China, we've done a lot of work in carbonate reservoirs and gotten very good correlations to production. The Permian Basin in the U.S., we use a similar technique called reflectivity decomposition, but we again rely on the polarity of the reflection. And we're able to map carbonate porosity much better that way. And we presented that at SCG last year. And again, we're looking for that negative reflection over a positive reflection. So, variations in carbonate porosity, especially if you're dealing with porosity pods and porosities coming and going, and you're below seismic resolution, the variations of porosity will show up very well on the minus 90 degree phase component.
Okay. Felipe Abraham Santana Roman has a question on the modeling was done only in clean sands. Does it have any limitation on applying the technique in shale sand, carbonate, or complex lithologies?
Okay, well, let's first of all stick with clastics. And in the case of clastics, the hydrocarbons will always lower the impedance. And so therefore, it doesn't matter, as long as you're below tuning, it doesn't matter how it's layered. It doesn't matter what the sequence of reflection coefficients are. It could be very complicated, and the hydrocarbons lower the impedance of the interval that's below seismic tuning, so it manifests as a thin layer, and it shows up in phase decomposition. In the case of carbonates, the hydrocarbon effect can be negligible, or if you have light hydrocarbons or the right pore structure, the hydrocarbon effect may be big enough that you could see it. But that is highly variable, and it is very dependent on the rock type itself. So hydrocarbon indication of all kinds in carbonates is always more challenging. If the hydrocarbon effect is small, any seismic response to that hydrocarbon effect is going to be small as well. So I can't promise this will work in all carbonates as a hydrocarbon detector. It's probably better as an indication of porosity in carbonates.
Gerardo Clemente has another question. Does the anisotropy correction introduce an effect on the phase response? And the analysis must be in time, or it can be done in depth?
Does he mean the anisotropy effect on move out or on reflectivity?
Gerardo, can you specify if you are talking of azimuth or what type of anisotropy?
And the reflection amplitude.
The reflection amplitude. So if we're talking about TTI, transverse isotropy, so hexagonal type of anisotropy, and the near offset effect is going to be very simple. That's going to be very understandable. And then as long as the anisotropy is not too strong, we use the Thomson parameters and we can predict how the reflection coefficient will vary with increasing angle. And we found as far as affecting the phase, as long as we're pre-critical, then what I've described is still applicable. The problem becomes as we go post-critical, because then the reflection coefficient becomes complex. And instead of just the sequence of reflection coefficients, you have to consider the phase of the individual reflection coefficients will have a phase associated with them. So in that case, a single interface would not produce a zero phase response. It would produce a phase associated with the phase of the reflection coefficient. So as we go towards critical and post-critical, it starts becoming very complicated, and I've assumed we're well pre-critical here. Of course, the anisotropic effect on move-out, since this process doesn't rely on move-out, it's a trace-by-trace process, that doesn't affect the phase decomposition.
We have a comment from Jorge San Martin, more than a question. that if the method works in the depth domain, in reality, the process should be run in the time domain because the wavelength is different.
Well, that's a very good point, and I've often complained about the wavelets I see on depth migrated data. For example, you'll look at the waveform at the top of SALT, and it's in depth, and it's a beautiful zero phase wavelet. Well, that's cheating, and the depth processors know that's cheating, but they do it because that's what the clients want. So I agree that the depth migration can produce phase distortions. But I'm assuming we're in the sediments. The depth migrators haven't, it's not a major contrast, so they haven't played any games. And therefore, the reflection coefficients are responding pretty much the way they would in the time domain. So yes, it would be more correct to do it in time, but I've seen cases where it's okay to do it in depth.
Jorge Alberto Guizar Alfaro, where does this method behave better? On low frequency or high frequency? And how improving resolution methods can improve the application of this technique?
Yeah. So that's a great question. It's kind of backwards. Like I said, to be a hydrocarbon indicator or to indicate anomalously low impedance, you have to be seismically thin. So that means you have to be low enough frequency to be seismically thin. If you went too high frequency, you'd be seeing, and you were resolving the layer, you would be seeing single interface responses. So we have to be low enough frequency such that these effects are manifesting themselves. Of course, if we go to too low frequency, we lose, all resolution, or we lose amplitude as we keep going to lower frequency. So it's very often a trade-off. And so again, what our guys will typically do is they will do spectral decomposition on synthetics and on the data, and they will try to determine the optimal frequency band for a given target that they should be using. So different targets may have different optimal frequency bands.
We have a question from Felix Alan Ramirez Cuellar. How well this method work for interpreting both allochthonous and autochthonous salt?
Again, it depends on the contrast. I can't really generalize. It depends on the contrast and impedance between the salt and the layers and above and below, and how thick the salt is. So I really don't have a generalization I can make distinguishing two different types of salt.
Question from Damaso Contreras. For pre-stack data, does it spend a lot of time? Calculation time.
Yes. So I like to think that it's worth it, and so if you have a cluster, we should run it on the cluster. But yes, everything has a cost, and to extract more information, unfortunately, we have to use more computer time. But that's becoming less and less of a problem.
We have a question from Martin Jimenez. Is AVO only an indicator for hydrocarbon, or it is also works for lithology indicator for tertiary rocks?
Yeah, I've been surprised at how well it can be used as a lithology indicator. In fact, did a project many years ago in Mexico, and Carlos will remember this one. This was in the Jurassic under the Cantarell field in distinguishing dolomites from shales. They have different VPVS ratios, and to our big surprise, the AVO attributes and spectral decomposition of the AVO attributes were very, very helpful in distinguishing those lithologies. Of course, the more well control you have to calibrate, the better.
Alfredo Guerrero, is it valid to enhance the frequency in seismic data using Q compensation in share reservoir? And what could be the implications?
Well, you know, basically what Q compensation can do is it could boost the high frequencies within your band. And so it depends on the signal to noise ratio at those frequencies. I mean, Q compensation is a linear filter. So at any given frequency, it's limited by the signal to noise ratio at that frequency. So you can get some benefit, but it's a matter of a trade-off between resolution and noise. If you try to boost too far, too high a frequency band, you'll just be blowing up noise. So this is why we like to use other techniques. We like to use inversion techniques to imply what's happening at those frequencies. So as opposed to Q compensation, yes, do some of that where you know you have, at frequencies where you know you have good signal to noise ratio. But to go beyond that, you basically have to use your seismic inversion techniques to infer what's happening at those frequencies.
And we have the last question from Jose Manuel Perez Bautista. What is the rate of success of this method to discriminate good from bad anomalies?
You mean hydrocarbons?
Yeah.
Hydrocarbon? I have to say, remarkable. We have clients in the Gulf of Mexico and in the deep water who run this on absolutely everything and will not drill a well without it. I can't give you an exact number because most of my information is anecdotal and the clients don't often share everything with us. But we know by the fact that they're using it. And in the presentations I've seen for deep water hydrocarbon detection, they always show the phase decomposition results, and they use that. And without a phase decomposition anomaly, they won't drill a well.
And John, a last request from the organizer, if you can stop sharing your screen.
Okay.
That was the last question. Thank you.
If I could figure out how to do that. How do I stop sharing?
You did it.
I did it? Okay.
Pues brillante exposición de John Castagna. Agradecemos a John y a la compañía Lumina por el apoyo que siempre han brindado a la Asociación Mexicana de Geofísicos de Exploración. Una plática por demás interesante, donde un tópico que la gente que hemos hecho, que hacemos procesamiento de datos y la gente que interpreta información sísmica, siempre es un paradigma, el hablar de las fases, si estamos en fase 0, si estamos en fase mínima, y hemos llegado hasta la etapa en que podemos obtener información que nos indique parámetros petrofísicos de las rocas a través de la respuesta de fase. Por favor, staff, ¿podemos proyectar el reconocimiento? Muchas gracias, John. A nombre de la Asociación Mexicana de Geofísicos de Exploración, otorgamos el presente reconocimiento por la brillante presentación Phase Decomposition Theory and Applications, el 20 de agosto de 2020, siendo la primera reunión de la Asociación Mexicana de Geofísicos de Exploración, la mesa directiva 2020-2022, es un parteaguas entre las dos administraciones, y de aquí arrancamos para adelante y esperamos que sea un buen augurio iniciar con una presentación de John Castagna. Thank you very much, John.
And thank you for having me. I appreciate it.
Y agradezco también al staff de Lumina, Carlos Moreno, y a Efraín, al doctor Efraín Méndez, por todas las facilidades para realizar esta presentación, al staff de la Asociación Mexicana de Geofísicos de Exploración en la administración de las comunicaciones, también un agradecimiento. Fuimos solventando algunos defectos técnicos que hubo. Afortunadamente se dio esto bien. Asumo que se dio bien por la respuesta en cuanto a preguntas que se hicieron. Y estamos a la orden. La gente de Lumina también está a la orden. Ya tienen un compromiso fincado con Pemex. Y eso nos garantiza que podemos echar mano de la tecnología en un futuro inmediato. No me queda más que agradecer a todos los que participaron en esta reunión y siendo las 20:32 horas, clausuramos el evento. Muchas gracias.